You are all welcome. Today we are continuing on our geospatial data analysis, and today will be a review of what we have learned before and also an application of it in a real-world scenario. So we'll be talking about spatial weights, which we have talked about before in some weeks past, and spatial lag, then how we can combine these two together to do an analysis like spatial autocorrelation. So and one major way to in using this tool is doing hotspot analysis, just like what we have done in previous class using ArcGIS. In fact, what ArcGIS done at the back end that we don't know is what we want to learn now. It creates a spatial weight for our data. It creates a spatial lag for our observation. Then you can now apply different tools. Those are the things we will be exploring in this tutorial tonight. So just as a reminder, when we are generating spatial weights, we have different type of it. We have the one we call contiguity, and contiguity spatial weight is define the matrix that decode connections between existence of common boundaries. So when there is an existence of common boundary between two observations, this type of weight decode how the degree of existence of common boundary. It makes it directly suitable to use with polygon. So today we'll be using a data set that is a polygon in nature. So by the time we get to point data analysis also in future, we also use point data analysis for this same purpose. So now, if two polygons share boundary to some degree, they will be labeled a neighbor. That is, they are neighbor of each other. This is just a review of what we have done before. So under this kind of weight, so this weight method of contiguity has to do with are you sharing boundary with me or you are not sharing boundary with me. Exactly how much they need to share is what differentiates the two approach we will learn today. And what are the two approach? We have Queen method and Rock method. This is just a review. Now, in Queen contiguity, under Queen contiguity, one criteria is very, very prominent. Two observations only need to share a vertex, that is 1 point together in polygon. Maybe 1 point just collide together, and then we can consider them to be a neighbor. So it now depends on your research work or the problem you want to solve, whether this type of contiguity will work for you or not, as we will see in a practical sense when we start now. So constructing the weight under this principle can be done running a code, which I will show us later. Now, the second one is Rock contiguity. And Rock contiguity is similar to, and in many ways, superseded by Queen contiguity. In this one now, as stated by literature, all your boundary, it must share more than 1 or 2 boundaries. So now, let's say the main idea in this one is what? Two observations are neighbor if they share some of their boundaries, not ordinary points, as we see in Queen contiguity. So, and this can be generated using this code. Yeah, and I will show you later on. Now, another set of weight generation is what we call distance-based weight generation. Now, in this distance-based, we consider the distance between the two observations before we can say whether they are labor or not. So distance-based matrices assign weight to each pair of observation as a function of how far from each other they are. How this is translated into actual weight varies across types and variants, but they all share that the ultimate reason why two observations are assigned some weight is due to the distance between them. So the closer you are to me, the more I can consider you to be my labor. So we look at it more. Now, we have different types of distance weight matrices. One of it is k nearest labor, as we always see in all our ArcGIS tools on the ArcGIS software. And this approach, we'll be using it today in our application. One approach is to define weight to take the distance between a given observation and the rest of the sets, rank them, and consider them as a labor k. That is exactly what k nearest labor criterion does. Now, to calculate k nearest labor, weight, we can use a similar function as before. That is, we call our weight and we call KNNN from data frame. We put our database there and we give it a shell or a window. Just like in ArcGIS, you create a shell for what you want to plot. Now, in this case, can be 5, can be 10. That means we consider 10 observations and juxtapose and see whether they are closer to the present observation or not. So those are the things we will be looking at. Now, after we have now gotten the weight, which represents W in this case, what are we going to use that weight for? One of the most direct applications of weight matrices is the so-called spatial lag. Now, the spatial lag is a given variable. Is a product of a given variable multiplied by this weight matrix. Now, in this example that we want to look at today, we'll be looking at the cases discovered in respect to COVID-19 in West Africa and Central Africa together, which include Nigeria. So I've already gotten a shapefile of West Africa. I get the data of the number of cases detected, those number of people they've released, the mortality rate. I will be showing us those data. Now I can do my analysis based on the number of cases they detect. That will now be representing my Y in these matrices, this equation. I will now be multiplying each of these observations for Nigeria. I will multiply it with the weight matrix that I have generated, and it will give me a variable. The variable who is giving me is a factor, and we call that factor spatial lag. So now, after we get spatial lag, one of the places where we use spatial lag is in spatial autocorrelation. So before I go into this spatial autocorrelation, let me quickly show us in practical sense how spatial lag works. Let me just use this example which I have already programmed here, because I still have a long way to go. What I've done in this equation here is that I have imported a matplot library inline because I want to be plotting on my notebook. Then I want to import cbol as SNN, as you can see it here. Then I import pandas as PD. I've talked about all this in my previous tutorials. Then I import partial.library. I import weight from that partial.library. These are libraries, these are tools that will help us generate weight. So the most important thing here is that I import weight function here. Now, I comment out this, I don't need it for now. So I also import GeoPandas as GPD. And I also import NumberPy as NP. Then I finally import Matplotlib so that I can plot my shapefile. Now, in this directory where I am working presently, I have a data of COVID-19 in West Africa, as you can see here. I prepare my data for this purpose. So now, if you look at this list, I use GeoPandas to read that shapefile, and I just put the absolute relative direct path to that file. This shapefile is located in Central and West Central Africa. So I will read in this shapefile. If I press Ctrl Enter here, it reads the data in. Then I can display information about the data. Now, one thing I do here, I index that data. Don't forget, I save what I read into this GB, that's database. Now, I index my database so that for easy query, I use ISOS, because if I insert a cell here and I say, I just display my database, and I run, you discover that these are the data we have. Here, just object 1, country. This is country colon. Last update. This data was last updated in March 5, 2021 year. Confirmed cases per each country: Benin, 6,000, deaths, 75, recover, active, incident reported. Then mortality rate. Now, where I'm going is this ISO 3. That's the country code for each of the country that belong to West Africa. So I want to index my data based on that country code. It's not serving as my primary key in this case. So that's why I show you this. Let me cut it out. Now, that is what I'm doing here. I index that data based on this, but I don't drop that column. I say it should include that column. That's why I say drop to be equals to false. That it should not drop that column. I need it. So if I run this, it gives me the information of all the feed I have, like the object ID, country, last updated, confirmed, death, recovered, active cases that they have at hand, incident, mortality, and so on and so forth, with the length and the area. Now, another thing which I want to do, let me insert another cell here, is that I want to know the coordinate system that my data belongs. And how do I do that? I will call my database and say .crs, that is the coordinate system. And now we run it, and you see that it's in geographic 2D WGS. Now, if I want to do analysis like this, I cannot be using geographic coordinate system. I will be having error. Just like last week, we had to reproject our data also to a projected coordinate system. So now I will reproject this data into EPSG code 3395. That is word marker. That is the coordinate system I will be reprojecting my data to. So now what I will do now is I will write this code, which is database.to_CRS. This will project my data. This code will project my data to this coordinate system and save it in database too. So let me run that now. Yes, I've run it. Then I can plot it. As you can see now, Nigeria is somewhere here. This is Nigeria here. So that's the data we are using for this day. Now, I'm now going to weight. Now, I want to weight this data based on the relationship of each country to each other. And I want to be using Queen method to weight it. Remember in our theory aspect where my slide the other time, I say Queen contiguity, consider you to be a neighbor, even if you have just at least 1 point sharing. If we are sharing just only 1 point, you are a neighbor to me. So that's what Queen contiguity is all about. So I run this now and they give me this. But you look at the output. Because there are some countries that are not connected to each other, like Satomine, that's STP is the code. It's not connected to some country. So it's forming a disconnected component in my weight. That's why it's giving me a warning that there is one island in my data. That is, it is not having any relationship with other data. So if I check with its code, if I query my weight with that code, you will see that it is empty, STP, and I run it, you see that it's empty. But if I query for Nigeria now, which is if I query for Nigeria, which is NGA, and I run it, you see that I have Niger having 1. When they have 1 as a value, that means they are my label. They are label. Then you have Benin Republic, which is also 1. We have Cameroon, which is 1. We have Togo here, TCD, which is also 1. So we have how many label? 1, 2, 3, 4. We have 4 label. So that's what weight actually does. Now, that is one method. Let's look at another method of rock contiguity. So here, I just call this function weight.rock from data frame data2, and I run it. Let me remove this. If I run it, you see, I still have that same warning of that same island for me, an island. In fact, it makes, if I use this weight directly in my data analysis, I will have problem because of those islands that are well separated. That means I cannot use boundary to really determine my weight in this analysis. That will take me to distance weight matrices. So, but before we go to distance weight matrices, we can query for labels of Benin. As you can see, we have Benin label, we have Nigeria, Togo, Burkina Faso, and so on and so forth. Now, let's quickly go to K-nearest label, which is based on distance weight matrices. And in this case, I just want to use 5 labels for it. So if I run this code, it will give me what? Weight distance. See the ID code. You say lib5 which is the library I'm using, weight distance KAN. So now I can query for Benin again. You will see that it will have increased because now I have several labels based on distance. And you see that this one is not giving me any warning like the other one. So I will prefer using this distance, how distance this country are to each other. Then, so when we are doing application now, I will tell you how useful this could be. Now, another thing which I want to do is I can query a single column, and my interest now is on the confirmed cases. And on the confirmed cases, let me insert a column here, another cell here, and I will just print out this. I just call database 2. Then I query for confirmed cases here. If I control enter, you see in Benin we have 6,000. In Burkina Faso we have this. Let me go to Nigeria. We have this big number. In Senegal we have this. So you see all these. You can query out your database from there. Now let me go back to the lecture to look at autocorrelation. So now we've looked at weight matrices, and we have looked at spatial lag. And spatial lag is just taking an observation. One of the observations is the number of confirmed cases. If we multiply it by weight matrix, it gives us a spatial lag. So what is the essence of calculating a spatial lag? One of the essence of calculating a spatial lag is getting the spatial autocorrelation. Now, what is spatial autocorrelation? Spatial autocorrelation has to do with the degree to which the similarity in value between observation in a data set is related to the similarity in location of such observation. We need to look at this very, very closely. Let's see. Spatial autocorrelation has to do with the degree to which similarity in value between observation in a data set is related to the similarity in location of such observation. That is, if you have a set of observation, what is the degree of similarity of your observation in a particular location? How can you measure the degree of similarity of that observation? Like now, taking for an example, we have cases of COVID-19 in Nigeria. Now, we observe it in several states. Can we say that the data we are having in Lagos is similar to the one they have in Oyo State, in Ogun State? How similar they are, that is what autocorrelation will help us to solve. So spatial autocorrelation relates the value of the variable of interest, in this case, number of COVID-19 cases, in a given location, let's say Nigeria, with the value of the same variable in the surrounding location. That is, let's be specific. Let's say in Lagos, we observe variable Y, which is the number of cases of coronavirus. How related is that data with other surroundings or neighboring states? Now, in the case of example, in the practical example we are looking at, that's West Africa. When we take Nigeria, the data we have in Nigeria, how related it is with our neighboring country? Does it have any correlation? So those are the questions that spatial autocorrelation will help us to answer. So now, the key idea in this spatial autocorrelation is this. The context is that spatial randomness is trying to look for spatial randomness. That is, the key idea in this context is that of spatial randomness. That is a situation in which location of an observation gives no information whatsoever about its value. Now, what spatial autocorrelation will help us to check is that the data we have, is it that they just figure out those data randomly? Does it have any spatial function, spatial correlation with the location? So what spatial autocorrelation will help us to solve is the issue of randomness. It will help us to detect if these data are just picking randomly, or they are as a result of an observation. And when you say so a data is as a result of an observation, that means it's not obeying a specific pattern like a random format. So in other words, a variable is spatially random if it is distributed following no discernible pattern over space. So if it is not a random variable, then it will follow a particular pattern. Like when we talk of disease, if you say the total number of cases in Nigeria is this, and we have some neighboring states that people move, let's assume that people move interstate, inter-country now. Does it have effect on other country? Because this is a contagious disease or sickness. So it should have a pattern of movement. If it doesn't have a pattern of movement, then we cannot call that number, we cannot ascertain that that number is really an observation, but rather a random figure. So now, spatial autocorrelation can thus be formally defined as the absence of spatial randomness. Let's note that. So it will help us to detect whether there is a spatial randomness or not, which give room for two main classes of autocorrelation similar to the traditional cases. So now, firstly, it will give us positive spatial autocorrelation. And we have positive spatial autocorrelation when similar values tend to group together in similar location. And we have negative spatial autocorrelation in this case when similar value, let me put it more highlighted here. We have negative spatial autocorrelation, and in this case where similar value tend to be dispersed further apart from each other. That's negative spatial autocorrelation. Positive is they were grouped together. They were in the same location. They were grouped together. So that is positive. That means they are very close to each other. And when let's say we have high value in a particular location, we cannot generalize that place is an hotspot for such an incident. So, but in the negative spatial autocorrelation, the higher value are sparsely located. That means we cannot say the place is an hotspot. Rather, it is just either in the medium or in the cold spot. So let's go to practical now on this. So let me go to one of the data I'm using. Let me drag this to
yeah. Look, we'll have less than 3 minutes. So
3 minutes. Okay.
Log out, I'll just do it, then everyone log in.
Okay. Yeah. So now, firstly, let me take you to my Jupyter notebook again. I will create another notebook for us so that we can do these practicals. I pray we finish today. So now, let me launch a new Control N. Let me launch a new file. Let me call that our class. Let me rename it. Rename. Let me rename it as practice or demo. Then I will give it an extension of .ipnn. That's for notebook. IPYNB. enter. So that means this is I'm coming. Oh, let me discard it. So I'm coming. Okay, let me just launch, and I don't want to. Let me launch a new notebook part. Yes, I can call it any name I like. Now, the first thing I want to do here is that I want to import all my library, which are these. So I will just copy it from here. And put it in this cell, Control V. So if I run this, you see it's running, it's importing those libraries which I need. It's just CBOM, PyDance, ESDA, GeoPandas, NumPy. So that's run now. I will add another cell. Then next thing is I will prepare my data. And in this case, I will import my data. I will read my data, which is this data here. I will just copy this code. I don't want to be writing it. So I don't want to waste our time. This data here about COVID-19. I will run it. Yes, that's copy it. If I want to read it now, let me add another cell so that you see what I've just run. You see this is the shapefile. So I don't want this. I don't want to dirty up my code here. Oh, let me leave it. Can reference it later. So now the next step is I've read in my data. Then the next step is I want to index my data so that it can easily be. So I want us to continue because we have a long way to go. So now what I want to do again is I want to index my data just as I've done here in the previous practical work, the same code. Yeah, sorry, I open a wrong data. Come in, let me check. Okay, COVID. Is this one I need? Let me close this. So I want to index this based on this primary key here, ISO. So let me just copy this, put it here, Control V. So when Control run, you see, it gives me information about my database, these are all my feeds. So from there, I can add another feed. And what's next now is preparation of my data for this analysis that we want to do. So now, before that, I want us to, if we like, I think we will be overlooking this place, but we just take, yeah, we are just only trying to call our data, put it on a base map, but that's not my focus tonight. I want to go to spatial weight matrices. I will prepare my spatial weight. Now, in this case, but before then, so that I will not run into error, I will have to project my data to a metric format. So, and that's what I've done here, because if you check the coordinate system, it will give you WGS. So I will be copying this code. I will project it and save it in database too, just as I've explained before. So I'll paste it here and run it. Now, that is a success already. So now we can plot it just as we have it here. It's still the same data. So we can plot it. Let me add another cell here. We can plot it here. Control V and run it. Oh, sorry. Copy wrong data. Let me see. Just database.plot. Copy. Then put it here. Then run it. Then, oh, what is happening? Sorry. I copy wrong data. I copy the point data rather than the. Oh, let me just quickly do that. It's supposed to be this. I read in the wrong data, so I will quickly correct it now. It should not give me points, rather it should give me a polygon. I want to use polygon right now. So if I run this again, then yes, it's giving me proper data now. So I can index it, rerun this. Now I've re-indexed it. Let me retransform it. So it's being transformed again. Then I can now plot it. Now it's giving me polygon data right now. Now, having done that, the next thing is I want to prepare my spatial weight. And in this case, I want to use the KNN, that's nearest neighbor, K nearest neighbor format, which I have done before when I was teaching. So I will just copy the code from this place. Yeah, I'll just copy this code. It will work properly for me here. So I have this, and I can run it. Yes, it has created a spatial weight matrices for me. So you can check the dimension of this matrix. You will discover it's a square matrix. So next thing in my agenda, if I like, I can query. Another thing I can plot is detecting those islands, but I don't want to do that. Let me go. I can drop the island if I have island, just as I'm saying the other time. So, but that's not my focus. Now, for me to do autocorrelation, I need to standardize my data. And I can standardize this data using row-wise standardization. So let us row standardize it to make every row of the matrix sum up to 1. So it's best to standardize our data in this format so that we have a proper and concise optimized results. So that's what I will be doing here. So let me just copy this code here, then I will go and modify it here. Now let me paste it. I want to standardize my weight. Now for easy use, let me put this as W. I will rerun it. Yes, so that anywhere I call W, you now see that it means weight. So let me rerun this. Now I have standardized that weight matrices. I transform it first, then I standardize it into row format. Okay, having done that, if I like, I can start querying those things, but that's not all. So let me quickly generate the spatial lag for it. So now, what did I want to do with spatial lag here? Firstly, I don't want to run into maybe mathematical error of multiplying big value, because if you look at here where I query for number of confirmed cases, which in this case will be serving as my observation. You see that they are big value. So what I want to do now is that I want to take logarithm of all these values. I will take logarithm of this value and it will give me something smaller value like this. So that is what I will be doing for this calculation. Let me go back to my to my notepad here. So I can say that log reading value as y equals to this. This will be my y value. So if I run this now, I want to print that y out. So let me put y underneath. If I run it, you see we have this value. Now, to generate a spatial lag, which is multiplication of my observation with my spatial weight matrix. So to do that, I'm looking for, I would like to create another variable which I will use. Let me go and modify this. I'm coming. Okay, let me modify this here. Remind me. Now, the variable I will be using, I will call width dot spatial lag. Then W, don't forget, it's my weight matrix. Then my observation, this is y. Now, I want to be saving this value into another variable, but I want to call it spatial lag y. Yeah, let me run it. If there's any error. Oh, it's an error. Okay, it's telling me that BR is not defined. Yes, I've not defined it really. Let me look at where. Okay. In this case, it will be my database. Sorry. Let me use my database, which is DB2. So it will work. I will append the value result. The result, you know, is a vector. I will append it to my database, and I will call it. Let me use spatial lag, or let me call it lag. Yeah. The column will be lag. Then let me run this. It should give me an answer now. So let's say to see what I have done, let me display my database again. Database 2 and run it. You see that here now we have lag value. You see that the spatial lag has been calculated at the head. After this geometry now, we now have the spatial lag calculated. Okay. Yeah, I think we are achieving our purpose gradually now. So the next thing in our agenda now is to now use it to calculate our spatial autocorrelation. In fact, we can do other statistical analysis by finding the mean, the standard deviation, and so on. So now let's go to global spatial autocorrelation. If we can remember very well in our last classes when we use ArcGIS, our tutor tells us that we have what we call global hotspot analysis and the local hotspot analysis. Also, in spatial autocorrelation, we have what we call global spatial autocorrelation, where we consider the whole thing as a whole. So, global spatial autocorrelation relates to the overall geographical pattern present in the data. Now, the data we have now, which is West Africa, we want to look at what is the overall pattern present in that data. So statistics design is a statistics designed to measure this trend and thus characterize our map in terms of degree of clustering and summarize it. This summary can be visualized or numerical. We can get a numerical value for it to represent it, and it can be visualized. So one way of doing this is using Moran plot, and that's what we'll be using now. The Moran plot is a way of visualizing a spatial data set to exploit the nature and the strength of spatial autocorrelation. It is essentially a traditional scatter plot, but more than a traditional scatter plot, because it has to do with spatial data right now. So, and in order to be able to interpret value as above or below the mean or the quantity in terms of standard deviation, variable of interest, we have to standardize by subtracting its mean and dividing it by the standard deviation. So Moran high, creating a Moran high plot is similar to creating any other scatter plot in Python, provided we have a standardized variable and calculate the spatial lag beforehand. We have already calculated our spatial lag. So we will try to plot the Moran high plot, which look like this. But let's look at it in the case of the data we are considering now. So what I will just do now, I will copy this code and go and modify it to suit our data here. Now, the first thing I want to plot, and I want to plot in 9x9 dimension. Then I will be using my library SNS to generate a plot. And I want to be labeling this plot with this. Let me just use this. Then my database is db2. CI is none. Then plots display standard leaves. Okay, let me see where I will use all this and come. I think they try to exploit here. Where they calculate the standard deviation. I think it's here. Oh. Sorry. Okay. Okay, let me run it with that. Let me see. They give me any error. Oh, I know. What is it saying? Okay. Let me change this value to what I know here. I will be using my 2 point now. I want to use number of confirmed cases as S variable. Then Y will be my spatial lag, which is lag lag. Let me see what that will give me. Lag. If I run that, let me see. Yes. So plotting the confirmed cases on spatial lag. Now, you see what it gives me. Now, the issue is interpreting. You see that we have highest value, almost 50% of the data fall above this range, fall above this line of dividing the range. So while we have only very scanty, and the one that are even highest, you see that they are clustered in one place, while we have scatter, like a scatter plot below the line. So let me look at you see, like in their own now, they have high, like in this place. But this, we are using different data here. This is not for COVID-19. This is another data entirely. But here we have high, we have a low point, and we'll see the way the data is being distributed. But in our case, based on the data we are using, you see how scanty it is. We have the high value almost cluster in one place, while we have the lower value scatter all around. So if I like, I may change this confirm to interchange my axes so that I can have y to be here and have s to be here. Let me see if I interchange like that. Oh, that one is better the way I put it the other time. Give me more look, better look of my plots. So that's how Moran-High plots look like. So now I can calculate the Moran-High, which is a value. So I'm coming. So now I will use to plot this Moran-High. Say Moran-High plot is an excellent tool to exploit data and get a good sense of how much value are clustered over space, just as we have seen in our practical now. You can see that cluster value are above. Now, however, because it is graphical device, it is sometimes hard to condense its insight into a more concise way. For this case, a good approach is to come up with a statistical measure that summarizes the figure. That is exactly what Moran-High meant to do. So now, what we will do now, we calculate our Moran-High using this code, which is a library we have imported before. So let me go back to this, my data. Let me insert another cell. Then I will paste this code here. Then I will modify it. My database is not BR, it's database 2. Then the column which I want to consider is the lag, that's spatial lag, together with the weight. So if I plot this, if I run this now, and let me tell you to print my Moran-High out and let me run it again. You see that I have my Moran-High objects displaying for me. So I can query this Moran-High by saying Moran-High.I, and it will give me the value of how spatially correlated this value of cases of coronavirus in West Africa is. So let me Control V this. I just call this object because it's an object. I call one of the attributes of it, which is the I value. Then I will run it. You see the value is giving me 0.23. Yeah, what can I derive from this value? It's telling me, okay, the value is highly correlated, spatially correlated, but it's not that much. Assuming it's 1 now, we say, oh, there's a spatial correlation, awful. But now we have 0.2. So we can depict what actually happened in this plot with this value. This value is telling us what is happening here. And you see that there's not too much correlation. So what I will like to do is that of Nigeria, concentrating of every state and see if there's any spatial correlation. So that's on that. Now, that cannot really give us what we really need. So we can also query out a lot of things. The most reliable p-value. What is the level of confidentiality that we can get from this data? So we can query that one also out by just, let me insert another cell here. Say Control V. That will give me the value of P. You see how confident this thing is? It's just 0.015. If we multiply this by 100, that's just 15%. So we cannot really say, to me, we cannot really say coronavirus is that serious in West Africa like that. So that's on that. So if you want to interpret, you can read more about p-value and just interpret it. So another thing we can do is we can plot this Moran high in a scatter plot in another format that will give us the how large, then in a better picture, how this correlation is being distributed. So I will just paste this code, which is Moran scatter plot M. So I just call this variable mi, which I have calculated inside this scatter plot. So, and you see, good. You see that we have those ones that belongs. We have only hotspots in some, just how many of them that are inside hotspots, because this side here, where my cursor is the hotspot area. That's places where we have higher value of coronavirus of COVID-19 cases detected. You see that this place, which is how can we call this, lower or low point, we see that we still have just only 2 observations, while we have more in this area also. So this is the scatter Moran I plot, which we can interpret better when we look at the degree of probability. So now that's for global view. So we can interpret the cases of coronavirus in West Africa in global view with that pattern. Now, let's look at the local spatial autocorrelation. That one will give us the big picture in the local view. So this is what I was saying the other time: high, low, then low, and low, high. So we will plot that same thing here in the local view now. Let me modify this code in my notebook here. May I have the data? Control V. Now, let me do some modification. Now, this is my plot. It will be 9 by 9. Then I have a replot here. If standard, here, I think I use another data. I use, when I was plotting the other time, I use confirm. Let me just copy this from here. Copy. Then I put it here. Then my database will be db2. Then you can now label for me. See where actually this rock plot will not really show, but by the time we calculate the Moran high for the local view now, we'll be able to see this thing very well. So let me create another cell and continue with the next step. So the next step now is to calculate my Moran high in the local format, looking at the local autocorrelation right now. So that will give me a better view of my data. Let me Control V here. So the database I'm considering is not BR, so it's DB2. And the column which I want to consider in that database is the lag. So with the weight, which is there. So if I plot this, you see it's running, still running. Yes, it has finished running. So now let me see the results. So I can see the number of quadrants, the edge. But I want to look at how I can see how cluster is. Let me start from here. Let me copy this code just to see the result of what I have done now. Control V. Now, break observation into significant or not. So now the observation, the result here, I want to break it whether it is significant or it is not significant. That's what this code is doing here. So anything, any observation that is less than 0.05, it will be classified as a significant observation. So database 2, change this. Then store the quadrants they belong to database 2 quadrants. So that's what I'm doing there so that I can easily plot it. Yes, it runs successfully. So now I can check those that are significant in the data by running this code, just calling my database and query my significant database 2. Let me query the edge so that it can give me the false. You see that in Benin Republic, we have false. It's because it's not significant. Then in Burkina Faso, false. In Cameroon, false. In Cote d'Ivoire, false. So we can display all of them and see. I just print the first 5. Let me display all of them. You see that in Nigeria, that's my interest. It's true. The effect of coronavirus is very significant in Nigeria. While in Ghana also, you see them, it's true. Where other places where it is not significant, it is false. So let's see this thing in a chart before our time run out. What can I do here? Let me create a cluster for it. Coming. I don't want to waste our time by querying other things. So I just want to see how the plot will look, the edge. Okay. That's called cluster. How did I create that? Sorry. Okay, let me print out the first 5 significant value, which is also very important. Then you can print out the quadrant they belongs. So you can see them in this format. So let me see the quadrant first. Then we now do that plot and see. Oh, sorry, my database is wrong here. Database 2, then I run it. See, now the first 4, Benin is 1. That's low, very low. Burkina Faso 1, Cameroon 4. That's very high a bit. So quadrant 4, quadrant 2, quadrant 1. So you can just query such a thing out. Now my interest is in plotting it. So we can create a list cluster map with splots. So let me save this code. We will create a plot with this. Let me insert a new cell and see how it is being distributed, just like what we are ArcGIS will give us. So I'm plotting this lizard, which I calculate here. This is my Moran high, which I calculate here by multiplying my lag with the spatial weight. And as you can see, if I plot this now, oh, the database is wrong. That's why I'm getting error. Database 2. Then let me plot. Now you can see high low. You see the area where it is high low here is in yellow. We see where we have just low high. Nigeria is part of it. Low high. It's not that too pronounced. We have low low. You see all this area, there's no significant number of COVID-19 cases detected. Why? No NS here. All these other area, they are just so too low that no real cases detected in this area. So that is how autocorrelation works. So with this pictorial view, we can see where COVID-19 is really pronounced. So, and it is in high low. In fact, we didn't have high based on this analysis, but we have high low, maybe analysis here. So you see that Ghana and Nigeria, I think we almost belong to the same place. So that's where we will be stopping today. I don't know if I have any question.
Okay, thank you so much. Do we have is there part 2 to this one, or?
No. We are